Hi, this is question number 16 in chapter 7. The question reads, a 12-kilogram hammer strikes a nail at a velocity of 8.5 meters per second and comes to rest in a time interval of 8 milliseconds. A, what is the impulse given to the nail? And B, what is the average force acting on the nail? In this particular question, you need to take a look at a quick sketch here that might help explain things. A hammer that's coming down, it's striking this nail, it's moving with a speed of 8.5 meters per second, and once it hits the nail, it comes to rest in 8 milliseconds. So we know a couple of things. We know the initial momentum of the hammer. That can be figured out with mass and velocity, and we know that the final momentum of the hammer is going to be equal to 0. So therefore, we know the change in momentum of this hammer from where it starts to where it ends. And the change in momentum of the hammer is going to be equal to the impulse of the hammer by the nail, which, as it turns out, will also be equal to the impulse delivered to the nail by the hammer. This is Newton's third law. Let's go ahead and write this up. We can say that the impulse delivered to the hammer by the nail is going to be equal to the change in momentum of the hammer, delta P sub h, and that's going to be P final minus P initial. And when I write this out, I can, in the second line, say that my final momentum of the hammer is going to be the mass of the hammer, m sub h, times the final velocity minus the initial momentum, which is the mass of the hammer, times the initial velocity. I can quickly recognize that the final velocity is going to be equal to 0, and I should also pay attention to this idea that this is the negative y-axis and that's the positive y-axis. So technically speaking then, my initial velocity of the hammer is negative. I'm going to do that this time. I'm going to kind of use the usual sign conventions for velocity. And my next line looks like this. The impulse of the hammer, I should say on the hammer, is equal to the mass of the hammer, and this is negative, by the way, because I'm dealing with this term over here on the right, times the initial velocity of the hammer, and therefore I get 12 kilograms, the mass of the hammer, times this negative 8.5 meters per second. And this negative sign that I have here cancels out with the negative sign in the velocity, and I'm going to get about 100 kilograms meters per second. And that's going to be the impulse due to the change in momentum of the hammer. So technically what this is it's the impulse on the hammer, but that's also going to be equal to the impulse on the nail. You could kind of think of impulse as force times time. This is Newton's third law, action-reaction force pairs. So whatever the force, the upwards impulse is on this hammer by the nail, it's going to be equal to this equal and opposite impulse in the other direction on the nail. So I'm comfortable here with the impulse delivered to the nail. It's 100 kilogram meter per second. They want to know the average force, and it's important to recognize why they use the word average in this case. If I were to make a quick graphical kind of representation of what the force versus time profile might look like, it's going to look something like this. So here's force on the y-axis, time on the x-axis, and we're going to see a curve that looks like this. We should recognize, maybe from your math classes, that finding the area under this curve can be done using the antiderivative or the integral. And I'm going to have some upper and lower limits of integration. This is going to be my lower limit. I'll call that A, and I'll call that B on my x-axis. So I'm basically integrating this force function with respect to this time axis, the x-axis, between A and B. For those of you who have seen this kind of stuff in your math classes, in reality, it's important to see that they're asking for an average force, which is going to be somewhere around here. So we're basically treating this as if it were a rectangle, even though it's not. We're taking whatever this blue shaded area is, and we're just kind of pretending that it's this rectangle. That's the area where this average force is this dashed line. It's just important for you to recognize that that's not necessarily, that's a kind of a gross approximation, if you will. And so I'll leave the graph as I've written here. we can simply use the impulse momentum theorem to say, all right, well, the impulse delivered on the nail by the hammer is going to be equal to the change in momentum, but more importantly, impulse is also equal to force times time. So I was immediately drawn to this because the definition of impulse in terms of force and time give me this quantity of force that really is what I'm looking for. We can see that in this problem I was given time, and so I should pay attention to that because ultimately I'm going to be substituting that in over here for time and basically solving for force. So let's go ahead and finish this problem. I can say the impulse delivered to the nail, which I've already figured out was 100 units, is going to be equal to the force on the nail times the time. And so therefore, if I divide both sides by t, I get this impulse on the nail divided by the time of contact is going to give me this average force. So I'm going to take these 100 impulse units, technically those are Newton seconds, 100 impulse units, I'm going to divide it by the time of 8 milliseconds, which is 8 times 10 to the negative 3 seconds. I'm going to get something on the order of about 13,000 newtons. 13,000 newtons being the answer to part B for question number 16.